This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 11 of Week 5. Plant efficiency, cogeneration, and the combined cycle. We start with one number. Overall plant thermal efficiency, net workout over fuel energy in. Turn it into heat rate, the utility's favorite metric. Then learn the two big tricks for beating a single cycle. Stack a gas turbine on top of a steam cycle, or harvest the waste heat as useful process heat. One number rules a power plant. Thermal efficiency, net workout over fuel energy in, which is also fuel heat in minus heat rejected, all over heat in. Its hard ceiling is the Carnot efficiency, 1 minus the cold reservoir over the hot reservoir in absolute temperature. Real plants sit well below it. A standalone gas turbine around 35 to 40%. A standalone steam plant about the same. The whole topic is about raising that number without breaking the Carnot ceiling. Keep one idea in mind. Every efficiency here is the same ratio, useful output over fuel in. What changes is what you count as useful output. Utilities rarely say efficiency. They say heat rate, the BTU of fuel needed to deliver 1 kilowatt-hour. It is just 3412 over efficiency, because 1 kilowatt-hour is about 3400 BTU of electrical energy. A perfect plant would have a heat rate of 3412, a good combined cycle around 6000, a simple steam plant around 10,000. Notice the inversion. Lower heat rate means higher efficiency. They move opposite ways, and that flip is exactly what gets missed. If a problem hands you heat rate, just invert. Efficiency equals 3412 divided by heat rate. A combined cycle bolts two cycles together, so the leftovers of the first feed the second. On top sits a gas turbine, a Brayton cycle, burning the fuel and making power. Its exhaust is brutally hot and would normally go straight up the stack. Instead, it pours into a heat recovery steam generator, an HRSG, which boils water. That steam drives a Rankine steam turbine for a second helping of power from the same fuel. One fuel in, two power outputs out. Modern combined cycle plants reach 55 to 60%, the best of any plant that burns fuel. The bottoming cycle adds no fuel of its own. It lives entirely on heat the gas turbine was about to waste. Here is the formula people get wrong. The bottoming cycle only ever sees the heat the topping cycle threw away, which is 1 minus the Brayton efficiency of the fuel. So combined efficiency is the Brayton efficiency plus the Rankine efficiency times that leftover fraction, 1 minus eta Brayton. That leftover factor is everything. If you just add the two efficiencies straight, you double count the fuel the gas turbine already burned, and you overstate the plant. Always discount the bottoming cycle by what the topping cycle already took. And note, this is a standard derived result. The handbook shows the combined cycle layout and the two cycles separately. You assemble it yourself. The variable table. Fuel energy input, Q in, fuel flow times heating value. Net electrical power, W net. Useful process heat, Q useful. Plant thermal efficiency, a pure ratio. Heat rate, the only one carrying BTU per kilowatt-hour. The topping and bottoming efficiencies, eta Brayton and eta Rankine. The cogeneration utilization factor, EUF. And recovery effectiveness, epsilon. Three of these are unitless ratios. Thermal efficiency, the utilization factor, and effectiveness. One caution on the fuel input. If your power is in megawatts, keep the fuel input in megawatts too. If you are given a fuel flow and a heating value, multiply them first. Cogeneration, also called combined heat and power, makes electricity and then captures the rejected heat as a useful product. Process steam, hot water, drying, all from one fuel input. Its scorecard is the energy utilization factor, net power plus useful heat, over fuel in. A power-only efficiency counts just the electricity, typically 35 to 45%. The utilization factor counts power plus heat and runs 70 to 85%. But that high number does not mean cogeneration is better at making electricity. It means almost no fuel energy is wasted, because the heat a normal plant dumps to a cooling tower is here sold as a product. Same fuel, two useful outputs. Like the combined cycle formula, EUF is a standard metric you bring yourself, not a boxed handbook equation. The recovery device itself is graded by effectiveness, actual heat recovered over the maximum thermodynamically possible. For a unit pulling heat from an exhaust stream, the maximum means cooling that exhaust all the way down to the cold side inlet temperature. So effectiveness is the actual temperature drop over that ideal drop. It can never exceed 1. Do not confuse effectiveness with plant efficiency or with the utilization factor. Effectiveness rates one component, the recovery device, not the whole plant. It is the same actual over maximum ratio you already use for heat exchangers in the effectiveness NTU method, because an HRSG, or an economizer, is just a heat exchanger on recovery duty. 2 short calculations, the 2 metrics that define this topic. Part A, combined cycle. A gas turbine topping cycle at 38% feeds a steam bottoming cycle at 30%. Find the combined efficiency and its heat rate. Part B, cogeneration. A plant burns fuel at 100 megawatts and delivers 35 megawatts of electricity plus 45 megawatts of process steam. Find the utilization factor and compare it to the power-only efficiency. The plan, for Part A, combine the 2 efficiencies with the leftover factor, then invert for heat rate. For Part B, add power and useful heat over fuel in, and separately divide power alone by fuel in. Apply the combining relation. The leftover fuel fraction is 1 minus 0.38, which is 0.62. The bottoming cycle contributes 0.30 times 0.62, which is 0.186. Add the topping efficiency back. 0.38 plus 0.186 is 0.566, about 57%. Invert for heat rate. 3412 over 0.566 is roughly 6,000 BTU per kilowatt hour. Check the trap. Naively adding the 2 efficiencies gives 68%, overstating the plant by almost 12 points. And the gas turbine alone had a heat rate near 9,000. A bottoming cycle pulled it down to about 6,000. Report 57% and 6,000 BTU per kilowatt hour. Add both useful outputs over the single fuel input. 35 plus 45 over 100 is 80%, the utilization factor. Now the power-only efficiency, electricity over fuel, 35 over 100, just 35%. The utilization factor of 80% is the fraction of fuel doing useful work, power and heat together. The power-only 35% is the only fair number to set against a power-only plant. That gap is the entire value of cogeneration. 45 megawatts of heat a normal plant would dump to a cooling tower is sold here as process steam. The fuel is 80% utilized, but only 35% efficient at making electricity. Never compare the 80 to a 40% power plant and claim cogeneration breaks thermodynamics. 4 traps. 1. Adding the 2 efficiencies for a combined cycle. The bottoming cycle only sees the rejective fraction, so it is eta Brayton plus eta Rankine times 1 minus eta Brayton. Drop that factor and you overstate the plant every time. 2. Comparing the utilization factor to a power-only efficiency. The utilization factor counts heat plus power. Match power only to power only. 3. Inverting heat rate the wrong way. Heat rate is 3412 over efficiency, so lower is better. If a better plant gives you a bigger heat rate number, you flipped it. 4. Confusing recovery effectiveness with plant efficiency. Effectiveness grades one device against its own limit. It is not the plant efficiency and not the utilization factor. Keep component and plant metrics apart. Bookmark the cycle pages. Thermal efficiency, network over fuel in, with the Carnot ceiling. Heat rate, 3412 over efficiency, in BTU per kilowatt hour. Lower is better. The combined cycle layout, with the Rankine and Brayton cycles, and the combining formula, eta Brayton plus eta Rankine times 1 minus eta Brayton. The cogeneration utilization factor, power plus useful heat over fuel in, and recovery effectiveness, recovered over maximum. Remember, 3 of these, heat rate, the combined formula, and the utilization factor, are standard results the handbook does not box. Bring them from memory. Only thermal efficiency and effectiveness have pages to point to. You now own the system-level scorecards, plant thermal efficiency, and its heat rate twin, the combined cycle stack that reaches 55 to 60%, and the cogeneration utilization factor that counts heat as a product. But every one of these plants still has to dump its leftover heat somewhere. In Topic 12, we follow that rejected heat into the condenser and the cooling tower, where it goes, how much cooling water it takes, and how the wet bulb temperature sets the floor. The leftover fraction you discounted today is exactly the heat the next topic has to reject. See you in Topic 12.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.